Because I know what you're thinking. High impedance electroporation. Right off, you're probably wondering, how did these guys come up with such a snappy name? And you're going to be surprised we don't even have a marketing department. So who we are, in fact, is a couple of partners. May-Ruben, I'm the Ruben. May is the scientist, I'm the business guy. And the parent company is Alberta Mining Corporation, which has been around for a while, and ironically started in the exploitation of resources. And now we're quite involved and focused on clean water and clean energy. And our job is to incubate new technologies, to get them launched and commercialized, but to stay in the actual technology development business and work through subsidiaries for the operators. High impedance electroporation. We do believe that this will be the first major breakthrough and transformation in 150 years since Louis himself first developed thermal pasteurization. And if we may be so bold, I do believe it will be a full replacement. It will not compete. It will not be side by side. It will replace thermal just like the transistor replaced the vacuum tube. And one of those reasons why, to understand why we think that, take a look at pasteurization today. This is a typical dairy situation. It is very large. It's very complex. It's very expensive to buy. An average Canadian dairy, $600,000. And it is expensive to operate in terms of energy costs and maintenance. Now, if we are successful with HIE, then in about 2 years or so, what you're going to see is that entire room of equipment replaced with this. It'll be something that you'll hold in your hand. It'll be a solid state wafer, silicon, or ceramic material with many thousands of small holes in it, all wired. And the implications of that are significant. To move from thermal to an electric field, we can save over 95% of the energy involved, and of course, so flows the energy costs along with the energy utilization. And that again is for 70 million, which is kind of a typical Canadian dairy. Now, the capital cost, we know from Tetra Pak what a quote is for the, we don't know what ours is going to cost. To do that volume, we need about a quarter square meter of wafer. We think we can do it for under 60,000, we hope so, but we don't know at this point, but it's going to be a significant difference from what it costs today. For our partners, particularly our British partners, they're far more concerned about the product than they are about the energy savings. They like their cheeses in England and they like it to taste very natural and proper. They also think that there will be a better nutrition, reliability, footprint. These are kind of things that are obvious with the switch to a solid state. So what is behind this? What is electroporation? It's actually been around a long time. It's a laboratory tool. It's used by microbiologists. And what they do is they take a small solution and they put a couple of bare electrodes into that solution. They run a current through it, and then that current creates a field across the organism. And when they create that field, then pores begin to form in the membrane. And it happens very quickly. This is an actual scanning photograph of the membrane with the pores being formed. And underneath from the time, you can see it happens in milliseconds. And the pores can be temporary if they want the cell to live and just put new material in it or take it out, or it could be permanent and lethal. Now, it didn't take long for industry to say, whoa, we want some of that. Because if we can have a non-thermal way to pasteurize, this could be very good. So a lot of companies from 95 to 205 spent a lot of money and a lot of good people involved. There was a research center at University of Ohio dedicated to commercializing electroporation. It did get off the ground a little bit. It got FDA approval. There was a couple of units out there, and we know some customers that used it for about a year or so. But by 2005, it was all abandoned. And they could not overcome the operating practical problems. There's nothing wrong with the theory. So what went wrong? And this is a classic example of what befalls us all. It's a paradigm lock. So they begin with the same technology, with the bare electrodes in a small solution, batch solution, and say, okay, but now we got to go to commercial scale. So what we're going to do is we're going to have very large solution. So we're going to need very big electrodes, and we're going to need a very big current to go through it. And now you begin to get all sorts of problems because you've got ohmic resistance, and the interface is problematic. You get electrolysis and all sorts of nasty things beginning to happen. And those were the things that really defeated it. So, 2005, my partner is looking at this and he says, well, you know, this is kind of silly. All of the benefits come from the field. All of the problems come from the current, the conducting current. Why don't we just have a field without a current? Put some insulating material on the electrodes, some sort of dielectric material, and see, it'll be a transient field, but we can create a field. As long as it's open long enough, it'll kill the organisms. And so that's the basis of our patent application and technology. And if we can do that, then all of the negative side effects are automatically eliminated. Now this is a tremendous photograph. This is an actual lactobacillus. At the moment it is being hit with, no, it's a cartoon. Okay, but it's just kind of a representative of the conducting current, bare electrodes, versus the notion of a thin film material that allows the field to proceed, but not the conducting current. So it's a simple concept. But in fairness to those that went before, they probably couldn't have done it a decade or two ago. Because that film, as it turns out, at the end of our studies, has to be a very thin film. And the sizes we deal with have to be micro sizes in order to bring the voltages down to manageable levels. And this is our goal. We want to save energy, we want to save GHG production, but we want to bring fresh tasting milk, just the way nature intended, right to the table. Now, there are other applications. We're beginning in the dairy, working with dairy as our first partner, but any of the liquid foods are candidates, particularly beer. We've had a lot of interest in that area, as well as sports drinks, etc., juices. Potable water in areas where there's large cities that the pipes are compromised. You could run this with a 9-volt battery slipped over the end of a faucet. Point of use might be a solution. Industrial holding tanks, Legionella, they need to be treated. We can do it non-chemically. Perhaps municipal wastewater, drip irrigation. Biofouling is a big problem. It takes out a lot of irrigation. And now we're really getting blue sky. But pharmaceutical, to do on a bulk basis, on a volume basis, what they were doing in small batch before, perhaps we can do and open up cells and allow some bath solution to go inside it. Who knows? What have we done to date? We did build a proof of concept. It was a very crude macro scale, very empirical. We didn't know where to start. We created a very strong field, 600,000 volts, I think, and used a very thick dielectric material. We were able to kill, we put some E. coli in, we were able to test that with absence of a conducting current, we were able to kill the bacteria. But the problem, we were creating a giant electromagnet that kept cracking the dielectric material. So we said, okay, let's stop and understand what's going on here. So we spent over a year, nearly a year and a half, 2 different models converging. Wayne was doing a mathematical model while we had Dr. Vlasic at George Washington University doing a equivalent circuitry as a SPICE, a computer simulation, and the 2 tied. And so we had predictability, and if you have predictability, hopefully you have science. And you have a design tool. And using that design tool, then we did a lot of work on optimizing. It dictated the geometry. As I said, we're talking, go small, young man. Make it as small as you can and still let the milk molecules go through. So we're looking at 50 microns, and then very thin film dielectric material. It also specified, because there's a trade-off between different parameters, and so we were able to optimize some of the 3 critical parameters that were involved. So at this point, we said, okay, we've done all this work. We want it endorsed. We went to NINT and paid them to do a report. Dr. Hebert did a 60-page report. Bottom line is the conclusion was that the assumptions appeared valid. They felt the science was good, and the bottom line, it should work. At that point, now we need to get a prototype built. We met up with a large dairy processor in England, quite excited about it, that has agreed to fund the prototype, which will be commencing probably in this next month at the Newcastle, INEX group embedded in Newcastle. So we think it'll be within a year that we'll have the prototype, benchtop prototype done. And In terms of a business strategy, there are 3 ways to get to the top of a big tree. I mean, you can climb, you can sit on your acorn, or you can make friends with a big bird. And in our case, what we've been trying to do lately is put together a whole flock of big birds. And we're starting to get some good traction. Dairy Crest is the largest processor in the UK. And actually, they called us in November. We didn't call them. They had heard about us. And they are very progressive. So they have agreed to put up 100% of the prototype funding. Dean Foods is the largest processor in the US. They are interested in working with Dairy Crest. Today, Dairy Crest has asked to be the sole funder at this point. But we want an international group for a big launch. We want this technology to become the technology to be used, the better milk. I just got back from China and I met first meeting with the head of R&D for Wahaha. And if you don't know Wahaha, neither did I, except that they are the largest drink manufacturer in China by far. They have dairy operations, but that's a small part. They also have water, tea, sports drinks, juices. And the initial meeting, there's a great deal of interest in being the joint venture partner in China and also manufacturing. And the beer industry, this is the most recent. We had a great talk with head of R&D with Molson's, who had followed the whole thing with low impedance electroporation, saw the benefits, knew Dr. Zhang, all the people at Ohio, was disappointed that didn't work because he said beer wants cold pasteurization. And so they've looked at our material and they're quite excited about getting involved. In terms of a business model, we like the Honeywell approach, which is give it away for free. And it not only overcomes sales resistance, but it ends up being a pretty good way to maximize your bottom line. So what Honeywell does is give, like with Fairmont up at McDonald, they gave them a free boiler and controls, but they got 85% of the energy savings every year. So McDonald got new boiler, they save 15%. So we're kind of suggesting is on that average dairy, that savings gets split up. Maybe we ask for 75% of the savings. And that would give us, for each one of those kinds of units, $100,000 a year as an annuity on a product we hope is $60,000 or less. So, you know, as a rollout, just assuming that we roll this out fairly slowly, my estimate is that there is the volume. We know the annual volume, but we don't know what's the average size. So just bear with me that they're all 70 million. So that's around 700 dairies of new units a year. 2 minutes. Oh, perfect. And so let's assume it takes 5 years to get to that point. But I think our value proposition is if you're putting in a new unit, you can pay $600,000. You can pay $140,000 a year for energy costs for something that's difficult to maintain. And you can have an inferior product. Or we'll give you this for free, and you're going to pay $100,000. And it's going to be reliable, and you're going to have great milk. And if we can't close that deal, we're not very good at our game. So that's it. Thanks.